यस हम ही है गुरुकुल हमारा।
Hello students, I am Priyanjali Mukherjee, Assistant Professor of Electrical Engineering Department of Narula Institute of Technology. In today's video, we will discuss how to construct the root locus for the system which have both real and imaginary poles. In the previous video, we have discussed on the systems which have only real poles. So these are the contents. In this video, we will discuss on the locus of the system with real poles and the complex poles, as well as we will discuss on the system which have the multiple poles at origin. Now, the root locus was actually introduced by Evans in 1948, and it overcomes the drawback of Routh-Hurwitz criteria, because the Routh-Hurwitz criteria does not give sufficient information about the relative stability of the system. That is the amount of overshoot and settling time. Sometimes the poor stability may bring the system to the verge of instability. And another drawback of Routh was that it does not help much in design problems when it is required to achieve the desired performance by varying one or more system parameters. Now, both these drawbacks has been overcome by this root locus technique, which is actually a graphical method for sketching the locus of the root in the plane as a design parameter of the system is varied. That is, the locus of the roots of the characteristic equation when gain is varying from 0 to infinite is known as the root locus. So, in the previous video, we have learned how to draw the root locus of the system which has the real poles. But here we will consider the real poles as well as complex pole of a system. So let us consider an open loop transfer function which is described by this Ks equal to K by S into S plus 6 into S square plus 4S plus 30. And the feedback is unity feedback, and here we will considering that it is a unity negative feedback. So Hs is given 1. So to draw the root locus of the system, first we can recall that the root locus is symmetrical about the real axis, and the number of branches is equal to the order of the characteristic polynomial. That means the number of the poles of the open loop transfer function. So here we can calculate the denominator part is equal to 0, and we are getting then there are 4 poles, and 4 poles are located at 0. By solving this one 0, from this term we are getting minus 6, and from this term we are getting minus 2 plus minus 3j. So there are 4 number of open loop poles. That means the root locus has 4 branches. Now, as in this open loop transfer function there is no zeros, so we can say that that the branch of the root locus will originate from the open loop pole location and they will terminate to infinite. So here we can see the pole location. The poles are located at 0, minus 6 and minus 2 plus minus 3j. Now we will check the points which are actually lies within locus or not. So if we consider any point in between 0 to minus 6, then this point, any point in between 0 to minus 6 have the number of poles plus 0 to the right hand side is equal to always 1. That means an odd number. So the point in between 0 to minus 6 will always lie in the locus. And from minus 6 to infinite will not lie in the locus. So next we need to find out the asymptotes, because the locus branches that will proceed to infinite to along the asymptote with the asymptotically angle. Now to calculate the asymptote, this depends on the m minus 1. So number of poles is here 4 and m is 0. So is m minus 1 becomes 3. So q will vary up to 0, 1, 2, 3. And n minus m just becomes 4. So by putting the values of q and the n minus m to this equation, we are getting there are actually 4 asymptotes, and these asymptotical angles are 45 degrees, 135, 225 and 315 degrees. Next, we need to find out the centroid of the asymptote. Now, the centroid is actually the point of intersection of asymptotes with real axis, and it can be calculated by the summation of real parts of the poles minus summation of real part of the zeros, and the whole thing will be divided by the number of poles minus number of zeros. So if we put all the values, then we are getting the centroid equal to minus 2.5. So from the centroid, it is an intersection point, and from the centroid, the asymptotes with real asymptotes will originate. Now next we need to find out the breaker point, which is actually nothing but a point at which the multiple roots of the characteristic equation occurs. So it can be obtained by finding out the solution of dkdx equal to 0. So we know the characteristic equation GSHS plus 1 equal to 0, or we can write the GSHS equal to minus 1. So putting the values of GS and HS and comparing it with minus 1, we are getting the k equal to minus of s to the power 4 plus 10s cube plus 37s square plus 78s. And derivating it with respect to s, we are getting the dkds equal to 4s to the power 3 plus 30s square plus 74s plus 78, that is equal to 0. So the solution of this dkds is equal to 0, it becomes s is equal to minus 4.2. To solve this dkds equal to 0, I have used the trial and error method. So at minus 4.2 is the breakaway point. Next, we need to find out the intersection of root locus with the imaginary axis. So from the characteristic equation, it can be shown that this Routh-Hurwitz table can be obtained. So the first is 137 and k, another is 10 and 78. So from these two lines, we can calculate the third line as to the power 2 line. That is like this: 10 into 37 minus 78 whole divided by 10, which gives us 29.2. Then k, and from these two lines, that means from s to the power 3 and s to the power 2 line, we can calculate s line by the same formula, that is 2 29.2 into 78 minus 10k whole divided by 29.2, which gives us 78 minus 0.34k, and finally s to the power 0 line becomes k. So according to the Routh-Hurwitz criteria, so to the system to be stable, the whole first column element should be greater than 0. So we can say that k is greater than 0 and 78 minus 0.34k is greater than 0. And for the condition of marginal stability, that is 78 minus 0.34k is equal to 0 and k becomes 229.4. So at the value of k equal to 229.4, this line becomes 0. So we need to find out the auxiliary equation from the previous row, that is from s to the power 2 row. So the auxiliary equation becomes 29.2 square plus k equal to 0. Now the base solution of the auxiliary equation, that is s equal to plus minus j2.98, actually the intersection point of the imaginary axis, and it can be obtained from the solution of auxiliary equation. Now for the complex poles, wherever the complex poles and complex zeros are coming, then we need to find out the angle of departure in case of poles and angle of arrival for the case of zeros. So here the poles, these are the poles and poles are the complex poles. So we need to find out the angle of departure from the pole minus 2 plus j3. And we know that the root locus is symmetrical about the real axis. That means the root locus above the real axis is actually the mirror image of the root locus below the real axis. So these two poles are the complex conjugate poles. So if we find out the angle of departure for the minus 2 plus j3 pole, then the opposite will be mirror image of the angle of departure for the first pole. So in this problem we are calculating only angle of departure for the minus 2 plus j3. So now to find out the angle of departure from this pole minus 2 plus j3, we need to connect with all other open loop poles and open loop zeros. So here only open loop poles are present, so we are connecting this minus 2 plus j3 with remaining poles by the straight line. Now we need to measure this angle. So you can measure this angle by using protector, or you can use the formula tan inverse y by x. So after getting this angle, we are getting these are 123.6, here it is 90 degrees and this is 36.86. And one thing you have to remember that always you will measure this angle with reference to 0 degree. So the total angle of departure from this pole becomes 180 degrees minus summation of all these three angles, which becomes minus 70.46 degrees. And after calculating this angle for the complex conjugate pole minus 2 minus j3, the angle of departure will be 70.46 degrees. So this is the complete root locus of the system which has the real pole and the complex pole too. So here we can see these are the pole locations at 0, then minus 2 plus j3, this one is minus 2 minus j3, and this is minus 6. And it has four branches. So from these poles are the real poles, whereas this minus 2 plus 3j and minus 2 minus 3j are the complex poles. So for these two real poles, when the gain value is increasing, both the locus will originate from the pole locations, that is from 0 and minus 6, and they are going towards the breakaway point. And the breakaway point has been calculated as minus 4.2. So at minus 4.2, both the locus following the asymptotical angle. And here the asymptotical angles was 135 degree and 225 degree. So these two are this light green line and this blue line. These are two locus branches for these two real poles. Now for the complex poles, it will go from the open loop pole locations, that is minus 2 plus 3j and minus 2 minus 3j points, and angle of departure becomes, this is for this one is minus 70.46 degree, and here also it is 70.46, and both can be measured from the reference line, that is from 0 degree reference. So after that it will follow the asymptotical angle 45 degree and 315 degree, and then by following these two angles, these are going to the infinite. So this is the complete tooth locus. There are 4 branches. One is this light green, another one is this blue, this green and this red. These 4 are the branches which are originating from the open loop pole location and terminating to the infinite by following the asymptotical angle. So let us consider another example where the system has multiple poles at origin, as well as here the system has a single 0. So let us consider another example where the open loop transfer function is k into s plus 1 and the denominator is s square into s plus 3.6. And here also we are considering that the feedback is unity feedback and feedback is negative also. So from this we can say there are 3 poles of the system, and poles are located as 0, 0 and minus 3.6. So here at 0 location there are actually 2 poles, and minus 3.6 location there is 1 pole, and 0 is located at minus 1. So according to the rules, from these 3 branches, 2 branches will terminate to infinite, whereas a single branch will terminate to the pole location 0 location, that is at minus 1. Now if we check, then any point between minus 1 to minus 3.6, so it has to the right, in the right hand side it has always even number of poles and zeros. That is summation of poles and zeros to the base point of right hand side is always 2. So any point in between minus 1 to minus 3.6 does not lie in the locus. Similarly, like the previous problem, we need to find out the asymptotes, and as the q is varying from 0, 1 and 2, and the difference between the number of pole and number of 0 is 2, because there are 3 number of poles and only 1 0. So the difference between number of poles and zeros becomes 2. So we are getting 3 asymptotes, and these 3 asymptotes are 90 degree, 180 degree and 450 degree. Next we need to find out the centroid. So centroid is nothing but the intersection point of these 3 asymptotes, and it can be calculated by the summation of real part of poles minus summation of real part of zeros, and the whole thing will be divided by the number of poles and number of zeros. So the real part of poles, summation of this real part of poles becomes 0, 0 and minus 3.6, so it becomes minus 3.6, and real part of 0 becomes minus 1, so it becomes minus 3.6 plus 1 by number of poles minus zeros, that is equal to 2, so it becomes minus 1.3. So minus 1.3 is the centroid, or the point minus 1.3, the asymptote 90 degree, 180 degree and 450 degree will originate. The next is the breakaway point. So breakaway point is the point and it can be obtained by the solution of dkdx equal to 0. So using 1 plus KSHS, that is the characteristic equation is equal to 0, we can find out the relation s to the power 3 plus 3.6 s square plus ks plus k equal to 0. We can solve this equation and we are getting that there are 3 solutions, that is s equal to 0 and the remaining 2 are minus 1.65 and plus minus j.936. So now this S2 and S3 are actually the complex quantity. So the S is equal to 0 is the actual breakaway point. So from the origin or S1 is equal to 0, the breakaway point occurs, that means two poles, from the 2 poles the locuses are coming to the breakaway point at 0 and then it will go to infinite. Next we need to find out the point of intersection with the imaginary axis, and to find out the point of intersection with imaginary axis we will take the help from the Routh-Harwood criteria. So first we are going to find out the Routh table from the characteristic equation. So characteristic equation is 1 plus GSH is equal to 0 and it becomes s to the power 3 plus 3.6 s square plus ks plus k equal to 0. And to find out the Routh table, we are using the alternative coefficients, that is 1 and k, and for the next line it becomes 3.6 and k. So after completing this Routh table, so k equal to 0 from the auxiliary equation, and the auxiliary equation becomes 3.6 s square plus k equal to 0. So the auxiliary equation when 3.6 s square plus k is equal to 0, it gives the solution s is equal to 0, which means that the root locus branches will not cross the imaginary axis. So this one is the complete root locus of the given system, where there are 2 poles at this origin. So these are the multiple poles, and another pole is located as minus 3.6 and 0 that is located at minus 1. So from this pole, that is minus 3.6, the locus will go to the 0. That means this red line, it has originated from the open loop pole location minus 3.6 and it will terminate to the minus 1 location, whereas these 2 poles will create the locus of this blue and green line, and after originating from the pole location, the breakaway point is 0, that means from 0 it is starting from 0 and again from the 0 it are going, these 2 are going to the infinite location by following the asymptote. Those were the 90 degree and 270 degree. So this blue line is following the plus 90 degree and this is the plus 270 degree, and these 2 are going to infinite. So it has 3 branches, one is the red one, another is blue, and third one is the green. So these 3 branches has been originated from the pole location, that is 0, multiple poles and minus 3.6. One of them has been terminated to 0 and remaining these 2 are going to infinite with following the asymptotic angle 90 degree and this is following the asymptotic angle 270 degree. So this is the complete root locus. So in this way we can plot the root locus of the system, that is by varying the value of gain k we can plot the locus of the root of the open loop system, and root locus is actually the locus of the roots of the characteristic equation when the gain value is varying from 0 to infinite, and that is the root locus and by varying the values of k, we can obtain the group locus, which is actually used to find out the stability criteria in field of the classical control theory. So these are the references. Thank you.
Hope after this video lecture you have a clear idea about today's topic. Now we will go through some questions answer session in the context of this video lecture. Now you are requested to go through gradually and try to solve the MCQ questions by your own. Answers are also attached at the end of the each question.